the first law of thermodynamics, and just to refresh our memory, there's really two equations that we need to know when dealing with our problems here. The first equation is the mass continuity equation. The change in mass of the control volume with respect to time is equal to the summation of the mass flow rates in minus the summation of the mass flow rates out. That is what we need to know. We also need to know this equation. The change in energy of the control volume with respect to time is equal to the summation of the heat transfer rates minus the summation of all the rate of work, so the powers, plus the summation of all the mass flow rates in times the enthalpy in, kinetic energy in, potential energy in, minus the summation of all the mass flow rate exitings times the enthalpy exiting, kinetic energy exiting, and potential energy exiting. These two equations are on your equation sheet. There is no need to memorize them because you're going to use them so many damn times they're going to be ingrained inside your memory. Okay? I want you to put these problems, when you see something is an open system, I want you to put these two things down on the equations that I need to use. And then ask yourself questions about every single problem, and you will eliminate variables here, and you'll get down to your equation for your problem. Some classes, some instructors ask you to memorize or look at the different versions of this equation for different systems. I just think it's a waste of your energy and your mind. Why don't you just look at it and be able to then analyze the system by taking this general equation and taking off what's there. That's what I think is going to be the best thing for you. But you do what's best for you. If you think that doesn't work for you, then do something else. But that's what I am going to keep with over and over and over again. Now you also have the additional equation that you can deal with, which is the ideal gas equation. PV is equal to mRT, or P times specific volume is equal to RT. Those equations can be used in situations where you have ideal gases. And then in particular, you're going to have the delta H is equal to C sub P T2 minus T1 when you're dealing with constant specific heats. Okay, if the problem says constant specific heats, that's what you're going to want to do. So I think if you have these four equations ready to go whenever you're doing problems, you should be good. Okay? Now, the constant specific heat method is a very valuable method for ideal gases. In fact, for air, it's almost exactly the same as a variable specific heat method, and so it's used quite frequently with really good accuracy. The two problems I have today that are dealing with air both ask us to do the constant specific heat method, so we will investigate that. And so here are the problems that I have for you. The first problem, what we're going to do is we're going to deal with a pipe. And this pipe is going to have, attached to the top outside of it, it's going to have some electric heater. An electric heater you're going to plug in to some power source. And then we're going to put that electric heater inside of insulation. Now what that's going to mean here, and it doesn't show very well in my picture, but that means that the heat is only going to go into the pipe, but not come out of the pipe. We're basically trying to say the direction of the heat is going to be into that pipe. That's what we're trying to say. And we're going to have, flowing through this pipe, we're going to have air. And there's a few things that we know about this air. We know it's state 1. And we know some information about state 1. And so we're told this. Air enters a pipe at 25 degrees Celsius. Temperature 1 is equal to 25 degrees Celsius. 100 kilopascals. Pressure 1 is equal to 100 kilopascals. With a volumetric flow rate of 23 meters cubed per hour. Volumetric flow rate at 1 is equal to 23 meters cubed per hour. On the outside of the pipe is an electrical resistor covered with insulation with a voltage of 120 volts. So we have here voltage is equal to 120 volts, and our current is equal to 4 amps. We draw 4 amps there. Now they want us to look at this problem and assume the ideal gas model, which we probably would anyway. We're not going to go through generalized compressibility and determine if this is an ideal gas or not. We're going to assume the ideal gas model, and we're going to assume constant specific heat. So they're saying to us, assume that C sub P is constant, and the value of that C sub P is 1.005 kilojoules per kilogram Kelvin. They want us to find A, the mass flow rate of the air in kilograms per hour, and B, they want us to find the temperature at state 2. So if I were to draw some things here, states, here's going to be state 1 entering and state 2 exiting. So that's a read the problem statement. I want T2, I should say, in Celsius. And there's a lot of things we have to do from the words to the variables. We have to understand that. That's a key thing. We have to be able to take out what they're saying to us. Now, this problem doesn't say anything about being steady state in the problem statement. But I'm going to assume it's steady state. I'm assuming the air is flowing through there. We're not in that ramp up period, or we're not in the ramp down period. We're in that constant period where air is flowing through this pipe. There's nothing to tell us otherwise. So we're going to assume steady state. They also didn't give us any height difference, and they didn't give us any velocity difference in the problem statement. They did give us the volumetric flow rate, which has velocity in it, but there's nothing in this to say that the air is going to speed up as it goes through the pipe. Nothing's telling us that. So we're going to say that kinetic energy is equal to potential energy, which is approximately equal to 0. It's not saying there isn't any height change or there isn't any velocity change to that pipe, but it's not significant. It's not going to be significant. Okay, so we take those things and we go now say, how do we solve this problem? Well, the first, to find the mass flow rate of the air, that's something we've done many, many times. If I went and did this equation, I know we're at steady state, so this goes to 0. The mass does not change, inside the control volume, does not change with time. And you might ask, what is your control volume, Dr. Wanklin? Well, I'm going to make my control volume this, and I will explain why I make it this and not just the pipe here in a second. But if I go look inside that yellow box, the mass of the air in that control volume is not changing with time. It's steady flow. If I take a snapshot over and over and over again, 1 minute, 3 minutes, 17 minutes, the mass inside that control volume is going to be the same. It does not change with time. And there's only one mass flow rate in, there's only one mass flow rate exiting, so I know here that m dot 1 is equal to m dot 2, which I'll just call m dot. Doesn't matter where we find the mass flow rate. If we find it at 2 or at 1, it's the same mass flow rate. And I know that mass flow rate can be found by taking the volumetric flow rate divided by the specific volume. And I was given the volumetric flow rate at 1, so if I find the specific volume at 1, I can find out what the mass flow rate is at 1, which is the same as 2, which is the same as the mass flow rate. If this was something besides air, I could look up the specific volume in our tables. This is air, so I'm going to use PV is equal to RT. Again, do not use this equation. Do not use this equation with water. I promise you on this next exam, there's going to be multiple people that is going to use the ideal gas equation, the gas equation for liquid water. It happens all the time. Don't be those people. Let that be somebody else, okay? Don't be those people. You may be tempted to use it, okay? Don't fall prey to that. Okay, so what we're going to do here, m dot is equal to AV, 1. We're going to solve for specific volume here. It's going to be RT times P, and this is all going to be state 1. We've done this before. This is nothing new. This is what we talked about on the last session, but still we have to work with it because it's going to be a part of now a bigger problem. Okay, so what's our answer here? We're going to put in 23 meters cubed per hour. Our pressure here is 100 kilopascals. Our R value is 8.314 divided by the molecular weight, which is 28.97. And this gives me units of kilojoules per kilogram Kelvin. Again, I took R bar, which is in kilomoles, and I divided it by the molecular weight so I can get it into kilograms. If I was doing this in English units, I would have a different R bar. My temperature they gave me was 25 degrees Celsius, and I know that I have to add 273 because I must have the values inside of this ideal gas equation must be absolute. And now before I do any calculation, before I type anything into my pretty pink calculator, I have to make sure that the units are correct. I'm not allowed to do the calculation until I check the units. Okay, so let's check the units. Kelvin goes away. Okay, I have kilopascals here. Let's check what kilopascal is. 1 kilopascal is 1 kilonewton per meter squared. Okay, so kilopascals go away, and some of my meters go away. And now I have a kilonewton times a meter. A kilonewton times a meter is a kilojoule. Kilonewton times a meter is a kilojoule, which goes away. And I have kilograms per hour. If we look at the units, if I multiply the bottom by kilograms and the top by kilograms, which is multiplying by 1, I get kilograms per hour. And that is what the problem statement asks. So now and only now I can do my calculation. Please get in that habit. I saw so many points left on the wayside because of this. And most of the questions I'm getting in my office hours are dealing with units and units only. They have good thermodynamics, but they have poor units. So please check your units. Please check your units. Now I can go through here. It would have worked out here in the situation. If I would just plugged and chugged, I would have been okay. I would have been. You'll luck out every once in a while, but don't make a plan to be successful on an exam about being lucky. That's not a good plan. Okay. 23 times 100 divided by 8.314 divided by 25 plus 273 times 28.97 gives me that the mass flow rate here is 26.89 kilograms per hour. That's my answer for part A. Again, something that we've done before. B, we want to find out what temperature 2 is. And you have to understand that sometimes to find a temperature, we have to use an equation. You can't just start looking in your equations for temperatures. You have to say, okay, I have to find this some way, and you might have to use an equation that doesn't have temperature in it that will eventually give you temperature. So if you get stuck on this, I think the one thing that you always should do is always go back to that first law. If you say, I don't know where to find it, let's go back to the first law and see what we can do. Okay, so the first law, the change in energy of the control volume with respect to time is equal to the summation of the heat transfer minus the summation of the work, the rate of work, which is power, plus the summation of my mass flow rates N times my enthalpy N plus my kinetic energy N plus my potential energy N, minus the summation of my mass flow rates X-ting times my enthalpy X-ting plus the kinetic energy X-ting plus the potential energy X-ting. Right now, I'm going to write out the whole darn equation. But you might feel comfortable at this time saying, hey, I already know things go to 0 here. I'm not going to waste the graphite to write it out, or the ink, or whatever, or the digital whatever you're doing. I'm not going to waste the hand motion because it's just too much. Okay, what do we know here? We know that this goes to 0 because it's steady state. The energy of my system, of my control volume, is not changing with time. It's going to be the same. No matter what snapshot I take, it's going to be the same. I know that the kinetic and potential energy effects also go away because I made that assumption, and I wasn't given anything in the problem statement that leads me to believe otherwise. I do have to think about this heat and work, because the resistor is creating heat. And there are two approaches I can make with this problem. Okay, if I look up here, the control volume that I created does not have heat. It has power or rate of work going into it. I could create another control volume which just that just had the air, that then it would be a control volume that has heat in it. Those are two acceptable ways to solve the problem. The reason why I chose this control volume is I can put it all in one nice equation. If I chose the control volume with just air, I would have to make a calculation about the heat and then put it into the equation for energy, which essentially is the same thing I'm going to do right here. It's just a little bit different mentality. So please understand, I could look at this as either having heat but no work, or work but no heat, and I can get the same answer. My perspective here is to say work but no heat. So I'm going to get rid of this. Now I have to calculate that work to put it in here. Work, or power, I should say. Keep saying power. I say work. W dot is equal to, well, we know for electric situations, it's going to be voltage times current. And we're given the voltage was 120 volts. And we're given the current is 4 amps. And if we remember for our conversions, we know that 1 volt is 1 watt per amp. We're very rarely doing things in watts or joules in this class. We're doing things in kilowatts. So I want to say that there are 1,000 watts in 1 kilowatt. And when I do this, I'm going to get 480 watts divided by 1,000. So I'm going to get 0.48 kilowatts. Now remember, when we do this calculation for electricity, it doesn't have a sign convention for us. We have to think about that. When we do the work calculation, integral of PDV, when we do the boundary work, sign convention pops out. That's the only thing it pops out on. This one, it doesn't. And we have to recognize that we're plugging this in externally into the system, so it's from the surroundings into the system. So this is going to be negative to work with. And so now what I do is I have this value here. I have all the work. I also have the mass flow rate in and the mass flow rate out. I know that. So let's rewrite this equation down here. Let's rewrite it. It's going to be 0 is equal to, I'm just going to say minus the work, the rate of work, plus my mass flow rate times H1 minus H2. That is what my big long equation simplified down into. Okay, and I found this sucker, and I know this. Now, if the problem statement asked me to do variable specific heats, I would have to go look up my enthalpies. And I encourage you to do it the variable specific way. Look up the enthalpies. In fact, you only look up enthalpy 1 because you know the temperature at state 1. You would solve for the enthalpy at state 2, and then go to your table and find the enthalpy and then read off what temperature that corresponds to. That's one way to do the problem. There's going to be a lot of interpolation with that way. Again, you would go to your table and you would find that this temperature here, you would look up the enthalpy here at 25 plus 273. You would find out what the enthalpy is. You would solve for H2. You would go to your table, look for H2, find out what temperature that corresponds to. But that's not what we're asked to do, because we are told to use constant specific heats, so we're going to replace this with C sub P times T1 minus T2. Now note, if it was 1 minus 2, I keep my temperatures the same way. T1 minus T2, I keep that the same way. 1 minus 2. Okay? So now I have 0 is equal to minus a minus 0.48 kilowatts plus my mass flow rate that I calculated earlier was 26.89 kilograms per hour times C sub P, which is 1.0055 kilojoules per kilogram Kelvin. And my temperature difference here, remember I can do it in Celsius or Kelvin because the temperature difference is the same in either of those, and I'm going to use Celsius here, so I don't have to do any conversions. 25 minus temperature 2, and this is going to be in kelvins. Now again, I cannot do a calculation unless I check to make sure that both things here, I have kilowatts here, I want to make sure I have kilowatts in this second part. So what happens here? Kelvins go away, kilograms go away, and I have kilojoules per hour, which is not a kilowatt. A kilojoule per second is a kilowatt, so I have to go here and say that in 1 hour, there are 3,600 seconds. I counted them last night. I know. I was watching a debate, and there was nothing better to do than count the seconds because that thing was a freaking trash fire. Okay. So, now we can add these two things together. Okay, so let's see what we have. We have 0.48 kilowatts plus 26.89 times 1.005 times 25. We're going to get plus 675 0.61 minus 26.89 times 1.005. Oh, I had to divide by 3,600 here. I'm making a mistake here. This one's going to be 0.0075 T2, and I need to make sure I do this right one. This one correct. 26.89 times 1.005 times 25 divided by 3,600, 0.1877. Okay, and I can solve for T2 here. Okay, so minus 0.1877 divided by 0.0075. I get a value here of 89.003 degrees Celsius. If I would have converted my temperatures to Kelvin, I would have got my answer in Kelvin and had to subtract 273 from that. But this makes reasonable sense, 89. I'm adding work into the system. My temperature should be higher than it was when I came in. Makes reasonable sense. I'll work with it, I'll go with it. Any questions on what we did there? Okay, let's do it again. This time we have a different type of control volume. We have a nozzle. Sorry, we have a diffuser. My diffuser looks like this. And it's an insulated diffuser, so I'm going to add some insulation to the outside of this. And again, we're going to have air flowing through there, air. It's going to have a state 1, it's going to have a state 2. And we're told the state 1, the air has a pressure 1 that's equal to 200 kilopascals. And the temperature 1 is equal to 325 Kelvin. And the area at 1 is equal to 6 centimeters squared. And the mass flow rate at 1 is equal to 0.5 kilograms per second. And we're told at state 2, the pressure of 2 is equal to 100 kilopascals. And we're told the velocity of 2 is equal to 250 meters per second. So let me read you the official problem statement. It says, at steady state, ding, Air at 200 kilopascals, 325 Kelvin, and mass flow rate of 0.5 kilograms per second enters an insulated duct having differing inlet and exit cross-sectional areas. The inlet cross-sectional area is 6 centimeters squared. At the duct exit, the pressure of the air is at 100 kilopascals and the velocity is 250 meters per second. Neglecting potential energy effects, ding, and modeling air as an ideal gas, ding. I should just say ding all the time. Maybe do that during the exam and see how it annoys the person next to you. They're 6 feet away. They probably can't hear you. Just say it. I mean, you could even say bong or something like that. I don't care. Bling, I don't care. So make a sound. Bring a bell with you. That would be good. That'd be really good. And modeling air as an ideal gas with constant C sub P. So now they're telling us we're going to say again constant C sub P. So constant C sub P, which is equal to 1.008 kilojoules per kilogram Kelvin. Determine, I want to find A, what the velocity of the air is at 1. And I want to figure out B, what the temperature is at the air of 2. Okay. It does actually ask me for C, which is the area at 2, but we're not going to have enough time to do that, and so I'll give that information to you that you can work through that yourself. Okay, so this follows the same pattern as the previous problem. Even though it's a different control volume here, we're going to go here and say, well, let's look at the air here. And for the velocity at 1, I know I have an equation that the mass flow rate at 1 has to be equal to the volumetric flow rate at 1 over the specific volume at 1. And I see that I have velocity right there. And I can find that because I know the area at 1 and I can calculate what the specific volume is at 1. Same problem, just a little different perspective. So I can say that the velocity at 1 is equal to mass flow rate at 1 times the specific volume at 1 all over the area at 1. And I know air is an ideal gas, so PV is equal to RT. So velocity at 1 is equal to m dot 1 times R1 times T1 all over P1 times area 1. And I'm being redundant by putting that 1 on everything because I just want to emphasize we can't take anything besides that state at 1. We cannot look at it anyplace else. We have to look at it at 1. And we're told here our mass flow rate at 1 is 0.5 kilograms per second. Our R value is going to be 8.314 divided by 28.97. This is going to give me kilojoules per kilogram Kelvin. The temperature at 1 is going to be 325 Kelvin. The pressure at 1 is going to be 200 kilopascals. And the area at 1 is going to be 6 centimeters squared. Okay? Now, we plugged things in. Now we have to check our units. We have to check our units. And so kilograms go away. Kelvin goes away. A kilopascal, just to refresh our memory again, and 1 kilopascal is 1 kilonewton per meter squared. So kilopascals go away. And I have centimeters squared and meters squared. I don't want that to happen, so I'm going to say that there are 100 squared centimeters squared and 1 squared meter squared. So now my centimeters go away, and now my meters are going to go away. And I look here and say, well, I have kilojoules, and I have kilonewtons, and a kilojoule is a kilonewton times a meter, and so my kilonewtons go away, and I'm going to end up with meters per second, which is what I need. And now that I have what I need, and I went through that rapidly, you might have to slow down and look at that a little bit. But I want you to get ready to go, pumped up from that, ready to go. Now we can do the calculation. So 0.5 times 8.314 times 325 divided by 28.97 divided by 200 divided by 6 times 100 squared is going to give me the velocity of 1 is equal to 388.63 3 meters per second. And I have to ask myself, does that make any logical sense? And it does, because this is a diffuser. The diffuser should come in, the velocity should come in higher than it goes out. And this shows me it's a higher velocity. So even though I'm not sure if the answer is 100% correct, I do know it makes sense that it's correct. If I got a lower number, 100 meters per second, that's not a diffuser. I would have been messed up. I would have had to go back and work on it. So this makes sense. I'm going to box it and say that's my answer. Okay, now let's find the temperature at 2. Temperature at 2, same sort of pattern that we're going to follow here. The change in energy of my control volume with respect to time is equal to Q dot minus W dot plus the summation of my mass flow rates in times my enthalpy in, kinetic energy in, and potential energy in, minus the summation of my mass flow rates exiting times my enthalpy exiting, kinetic energy exiting, and my potential energy exiting. I had a stamp, I just stamp it in there. And go for it. Yeah, go ahead. If you get one printed up, you can use it. I'll allow it. I should grade with stamps. That's what I should do. So this is going to be equal to 0. Steady state. Energy is not changing with time. Potential energy is not changing. No appreciable height difference. It's an insulated duct. No heat transfer. Coming into that heat, going into that control volume, there's no power, no electrical power. There's no shaft. There's no boundary change. There's no work. So I'm left with this. 0 is equal to, and I also know my mass flow rate is equal to my mass flow rate out. I haven't officially done a continuity equation, but I know I can do it in my head. dm, the change in mass of the control volume, is equal to 0. Summation of the mass coming in has to be the summation of the mass going out, and there's only one inlet and exit. So I can write this as m dot times h1 minus h2 plus v1 squared minus v2 squared all over 2. Now this equation tells us something. It tells us that either my mass flow rate has to equal 0 or everything in this brackets has to equal 0. One of those two things has to occur. And we know mass flow rate's not going to equal 0. It's just not. There's going to be some mass flow rate coming through here. So that means what's under what I have in the square brackets has to be equal to 0. So I say 0 is equal to, and I do this H, because it's a constant specific heat problem, is going to be C sub P times T1 minus T2 plus V1 squared minus V2 squared all over 2. Now here is where students sometimes, when I give the problem like this on the exam, they go, ha, Wanklin, you are trying to get me. Because you just said there C sub P, specific heat at constant pressure, and I can read this problem isn't at constant pressure. It goes from 200 kilopascals to 100 kilopascals. And then they go through the situation and they convert C sub P to C sub V and they put that in the equation. And it's completely wrong. Okay? Don't worry that this is not a constant pressure problem. It has no bearing to this. Delta H is always C sub P delta T, no matter what. Delta U is C sub V delta T. It does not matter if the problem is constant pressure or not. You need to make this replacement. Okay? So let's go and put some values in here. 0 is equal to 1.008 kilojoules per kilogram Kelvin times my T1, which was equal to 325 Kelvin, minus my T2, which I don't know. This is in Kelvin, plus my velocity 1, which was equal to what I just calculated here, 388.6. And then I have here squared minus my 250 squared, and this is all going to have units of meters squared per second squared over 2. Now again, I have to check my units. My first term has units of kilojoules per kilogram. My second term has meters squared per second squared. I cannot add those two things together until I can make sure their units are the same. So, what I'm going to do here is a little trick. I'm going to say that 1 Newton is 1 kilogram meter per second squared. That's multiplying by 1, but in a slightly tricky way. You would do a very similar thing with English units. Okay, so meters go away, seconds go away, one of my meters go away. I have Newton meters per kilogram, which means this is a Newton meter is a joule per kilogram. I don't want joules per kilogram, I want kilojoules. So I'm going to say that 1,000 joules is 1 kilojoule. And now over here we have units of kilojoules per kilogram. Now we can add these two things together. And we can solve for temperature. Now I want to get through another problem here. So I'm going to just give you the answer that T2 is equal to 368.9 Kelvin. That's the answer when we go through the algebra. I think you could figure that out, just look at it in your calculator. So the temperature does go up. Slow things down, temperature goes up. And I will also tell you that the area of 2 is equal to 21.2 centimeters squared. So these are the two answers. You can check this one with this calculation, and this one you can use that mass flow rate is equal to AV over V, and you can now go with state 2, knowing that this is equal to state 1. I trust that you can do that. But I want to get on to one last problem that kind of changes things up just slightly, and that is of a nozzle. So here we're going to have a nozzle, and it's insulated. And what's flowing through this nozzle is not air, it is R134A. Go from state 1 to state 2. And here's what the problem statement says here. Refrigerant 134A enters a well-insulated nozzle at 14 bar, so state 1. Pressure 1 is equal to 14 bar. 60 degrees Celsius. Temperature 1 is equal to 60 degrees Celsius. With a velocity of 37 meters per second. Velocity 1 is equal to 37 meters per second. And exits at 1.2 bar, so state 2. Pressure 2 is 1.2 bar. And a velocity of 460 meters per second. Whoa, we really sped up there. Velocity 2 is equal to 460 meters per second. For steady state operation and neglecting potential energy effects, which we would already think about those two things, determine the exit temperature. Once again, we're trying to find the exit temperature. We've done the same thing today 3 times. Okay, this time it's not an ideal gas. So what we're going to do here is we're going to write our equation. We're going to say the change in energy with control volume with respect to time is equal to Q dot minus W dot plus the summation of my mass flow rate N, enthalpy N, kinetic energy N, potential energy N, minus the summation of my mass flow rate exiting, enthalpy exiting, kinetic energy exiting, and potential energy exiting. For this control volume. And we're going to go through there and systematically go through all the things that we can go to 0 and we can neglect. Okay, so it's steady state, so this goes away. It's insulated, so this goes away. There is no electrical power into it, there's no shafts going into it, so this goes away. There's no potential energy, so this goes away. There's only one inlet and exit, so I can get away with the summation because there's only one. And I'm left with the same equation, 0 is equal to mass flow rate times H1 minus H2 plus V1 squared minus V2 squared all over 2. Same equation we had for the diffuser. And so, you could say, well, why don't I just memorize it? Because for darn sure on an exam, I'm going to put I'm going to say it's not insulated or something like that. I'm going to change it up just slightly. Okay? I will do it I'll take the same problem I gave to you right here in SI units, I'll put it in English units and see if you know what to do with those English units. Okay, because that does mess things up a little bit. Know what to do here. We have the same situation that our mass flow rate has to equal 0 or everything in this brackets has to equal 0. We know the mass flow rate's not equal to 0. So we're going to have 0 is equal to H1 minus H2 plus V1 squared minus V2 squared all over 2. And here is where students desperately look at this equation and say, I need to find temperature, and there's not temperature inside of this. There's not temperature inside of this equation. I can't solve for it. I need to solve for it. But what we have to do here is we're going to solve for H2. Okay? Because if we can determine H2, we know the pressure at state 2, we know the enthalpy at state 2, we know two things to set the state, and once we know those two things, we can find all the rest of them. We can find all the rest of them. So let's go through this and let's find out what H1 is. And so I have the tables here, my trusty tables, and I know that it said that we were at 14 bars, 60 degrees Celsius. Okay, so I'm going to go down here and I'm going to do this in my head. I know that I saturate at 14 bars, which is a line that's going to go up like this. At 14 bars, I saturate. I go across the vapor dome at 52.43. I'm at 60, which is above that number, so I know that I'm going to be a vapor. This is from table A11. I always start here with saturated properties. Now that I know I'm a vapor, I'm going to go to the next table A12, and look for 14 bars. 14 bars is right here at the bottom, 14 bars. And I see that there's a nice entry for 60. And so now I know that my enthalpy is going to be this number right here, 83.10. Okay, table lookup. What did I say? 283.10. 283.10. I know I'm not on the screen for those of you at home, but I'll be there in a second. Okay, now I got to put in my velocity information here. Plus, my velocity information is going to be 37 squared minus 460 squared, and that's going to have units of meters squared per second squared, divided by 2. I really wish, and I should have been smart and picked a problem in English units today, because we're pretty comfortable with this here now. We know that if we take this and we say that 1 Newton is 1 kilogram meter per second squared, I know that I can do 1 kilojoule is equal to 1,000 1,000, let's see here, 1,000 joules. I'm going to beg of you to do this problem in feet squared per second squared and see how you would get this to be BTUs per pound mass. From feet squared per second squared to BTUs per pound mass. You need to know how to do that. I can't remember if my homework has you do that or not. You need to know how to do that. Okay, so this, was there a question? So this is going to give you a negative number, right? Okay, so what this is going to get, and I'm running out of time, so I'm going to do this just quickly here, is going to give me 177.98 kilojoules per kilogram. That still doesn't give me a temperature. But I know I'm there and I'm at 1.2 bars. So just like everything else, I'm going to go to 1.2 bars here. 1.2 bars. I'm going to start out just like I do with anything else. 1.2 bars in saturation. 1.2 bars, and I'm going to see what are my limits. I start as a saturated liquid at 21.32. I end as a saturated vapor at 233.86 in my enthalpy. I'm at 177.98. I'm between these two numbers, which means I'm on the saturation line, which means that my temperature is negative 22.36. So it comes in at 60 degrees Celsius, and it goes out at negative 22.36. Okay? This is what refrigerants do. You put them through a nozzle, they lower the temperature a lot, and that's why air conditioning happens. And that's why you're comfortable, because of just going through a nozzle. That's why we do it. So that's the answer. Now, this problem didn't ask us to find out what the quality is. We didn't need to know about the quality. It just asks us what the temperature is. So negative 22.36 is the answer. Okay, that's 1:15. I have to get you out of here. If you have questions, please don't hesitate to ask them to me. I do not have my office hours today because I'm taking my kid to the orthodontist, and I'm busy filing police reports about my loss of identity, which sucks, by the way, which sucks. When that really sucks. Don't do that. I don't know if you can not do that. It just happens, but God, it sucks. So if you want to steal all my passwords, I've been changing them in the last few days, and my credit cards are all frozen. What else? My bank account. I go out and I don't know. You don't care. Go, leave.